last week you did the LightBot lab, and today we're going to follow up on that to discuss the concept of functional abstraction. So computational thinking is how we're going to do things in this class. It's not so much about learning facts in this class. It is about applying computational thinking to solve our problems. So computational thinking is all about thinking abstractly. In fact, you will see three techniques here that applies computational thinking. First of all is decomposition. This is closely related to the stepwise refinement that we talked about last week. Secondly is pattern recognition. Functional abstraction means the ability to recognize that a pattern is going on. And you'll see a very good example of LightBot and pattern recognition later in the video. Finally, now put it all together and write the step-by-step solution to solve your problem. And that is an algorithm. An algorithm is a sequence of steps that solves the problem. Note that computational thinking is not the same as thinking like a computer. What is programming? Programming is simply the act of directing the computer to do something. And as you did LightBot 2, you saw that you were directing the LightBot to do something. So many of the elements that you did last week in the lab are properties of programming. Two properties of programming that I want to point out that you did with LightBot are the sequence control structure. You will find out in a few weeks that we have three basic control structures for writing all our program. A control structure is simply the flow through the instructions that you are giving in your program. So the most easiest one to write is sequence, which means you do step 1, then you do step 2, and then what's next? Of course, step 3. You sequence through each instruction and execute them. Another thing you may recall that you did with LightBot is the function calls F1 and F2. And those functions are actually an application of abstraction. So as an experienced LightBot hacker, let's look at what you were doing. First of all, you were commanding the robot through this little block world, and that's what programming is. It is commanding an agent. So an agent could be, for a program, a computer, but it could be a person, it could be a device, an animated robot. So an agent will follow the commands or the instructions flawlessly as you give them and only do exactly what you tell them to do. So sometimes that's what makes programming difficult, is you leave out steps. The computer does not assume that you left out a step and do it for you. So the program implements human intent. As you were doing LightBot last week, your goal was to have the LightBot reach all of the blue tiles, but it would only do it based on the instructions you gave it. So if you ran your program and you saw that the LightBot did not hit the blue tile and turn it on, hopefully you can see where your instructions were wrong and make that correction. And that's known as testing. Again, we've talked about sequencing control structures. And so here we have the sequence of commands that made LightBot jump down 4 steps and turn on this blue tile. First of all, the number of instructions available is very limited. In this example, you'll see that you only had 5 instructions to accomplish this goal. And in computers, there's only so many instructions that it understands. That set of instructions is called the instruction set. It may be 50 to 100. So how can we write so many different programs? Well, it's the combination of instructions in different order. Just think about music. Really, we have 12 notes. A sharp, B, dot, 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 up to G sharp. And yet, we can write many, many, many songs, and the same thing with programming. An instruction is executed one at a time. I also want to point out a few other things. Right here, this would be called the program counter. We're going to get to hardware and inside the CPU in a few chapters. And so this, where it says calls and LightBot, it will be our program counter. It's pointing to 1, 2, 3, 4, 5. This is the instruction it is executing right now. I mentioned in the previous slide the term instruction set. Now, those instructions in the instruction set are known as machine language instructions. They can't get any simpler. That's the most simple task. It's exactly one task. However, we no longer program in machine language. We program in more high-level languages. And you will see one instruction for me as a programmer may actually be several series of steps for my agent, which is the computer. To a programmer, an instruction is monolithic. To me, I think, well, that's one instruction. It's one thing. But let's take a look at this instruction right here for LightBot. Is it monolithic? So I have that instruction executed here, and notice that the bot is in between. There must be two parts at least to that instruction, because one part turns on this light above his head, and he's done that part, right? The agent is actually doing multiple instructions. He's performed part of that and has not yet done the second part of that instruction, which is turn that blue tile into yellow. So to the agent, each instruction could be a series of steps. So that, for us programmers, is actually an abstraction. You don't have to think, turn on this halo light, turn on the blue tile. You just have to apply this one instruction right here. So that moves us on to this concept of functional abstraction, which means we're going to give a name to a series of operations that performs, to me, one coherent activity. One name, to me, but more than one instruction. It completes one task. To the agent, it's many tasks. This is a very powerful part of programming, and it requires that pattern matching ability. It requires that decomposition ability, and then forming it all together into an algorithm. All that stuff we mentioned earlier about computational thinking. Let's see how LightBot did that. Functions package computation. So in this case, we have LightBot here. And LightBot in this program is calling F1. And what is F1 doing? Well, where LightBot is right now, he's going to turn. So he will now be facing that way. Then he'll jump 2 times. We're on a blue tile. So we do the command to light the blue tile to yellow. And we're done. That's what we wanted to do. But he's facing this way. So I need to tell him to turn. So we're going to turn him that way. Right here. He's still not, but to jump down, I don't want him to jump here or jump down here. I'm going to turn him again. So he's facing that way. And that's what this command does. And then back down twice. Now when he lands, he'll be facing out that way. If you notice, let's call these a riser. All 3 of these are the exact same set of instructions. What F1 is doing is processing that set of instructions, and we're going to give it a name. We're going to call it process a riser. So let's say we have another riser here. Do you have to think distinctly of these 8 steps? And the answer is no, because you've already done that. We're going to think process a riser. In fact, equivalent name in programming is process riser. One thing about naming functions is you'll notice we're not going to do any spaces in the names. Because we don't do spaces, how do we read this easier that it's 2 words? We'll just capitalize. It's called Pascal casing. Pascal was a mathematician from 1700s, I believe. And also, at the end of this function name, I have a pair of parentheses. Now, this pair of parentheses is used for what we call parameters. So it's extra commands that we can send to the function that it can execute. So what if the set of risers may be more than 2 steps? How many steps will this one work for? Exactly 2. That's it. But what if I can say 4 here? So that is considered input into my function. And somehow, I'm going to think a little bit harder, how can I make it use the input that now it's going to do 4 steps instead of 2? And I'm going to jump ahead. That's going to be a loop, okay? So I might send 4 and loop 4 times, and the next time maybe there'll be 8 steps and I'll loop 8 times. By adding parameters, you see we increase the flexibility. So if you didn't quite get that, we're going to cover it a lot more later, but a little heads up on naming functions and the concept of parameters. Parameters are simply input. When I write this program now, what I'm going to think of is process riser. And when we get down, well, we need to move to the next step. And process riser, and we get down, and that's what we've got here. Process riser, which is F1 in LightBot, move to the next riser, and we did that multiple times. So now F1, or process riser, is the concept I need. I've just simplified my programming to 5 steps if I can figure out the steps to this. Okay, so remember last week when we talked about stepwise refinement? That's what we're doing here. Hey, I haven't thought about it yet, but now I'm going to think about what are the steps to move to the next riser, and let's see if there's a pattern for that. I'm going to call that, if I use my actual function names in programming, move to next riser, and there's my set of parentheses. In LightBot, we have to call it F2. There's no way around that one. So there it is. It's written. Here we have, at the beginning of the program, before the run is executed, we're going to do F1, process, F2. So what's F2 going to do? When he comes down, remember, LightBot is facing this way. So we're going to turn him so he's facing that way, and then we're going to just take 2 steps. We're done with that function call, and then we'll call F1 again to turn that one on, and repeat, repeat, repeat. How easy is that? So now my main program is just 5 steps. So did you see the idea? And I've got, how beautiful is that? To the programmer, the instruction is monolithic. To the agent, we have a series of steps. And it is one concept here, F1, but actually F1 is actually going to be 8 instructions. So functional abstraction is formulating blocks of computation and then giving it a name. So the programmer, after they formulated that block, just needs to think of that name instead of the individual tasks within there. Here's what we did. We spotted the pattern. We solved that using a sequence of steps. Then we put that solution into a package, process riser. And we created then this new higher level concept that's easier to talk about than turn, turn, jump up, turn on the light, turn, turn, jump down, jump down. That is what process riser is. Do you have to think about that anymore? No. Then we can use that to solve something a little even more complicated. Look at this. Have you heard of MC Escher? What if you had to solve this last week? I would be a little overwhelmed if I didn't have functions to do that. But now that I have functions, I think I can quickly solve this problem. So a function is just the packaging. Is there only one way to do it? And as a teacher programming for many years, I know that there are many ways to approach the solution to a problem. Even a simple problem can be solved in multiple ways. So here is another technique used to solve this same problem. Still requires 2 functions, but notice that it's packaged a little different. And this function, the first thing that's executed is F2, but what does F2 do? It executes F1. You may have noticed a pattern of turn, turn, jump, jump, turn, turn. Well, F1 now has simplified that. And we put the fact that we're doing that twice into F2. Looking ahead, chapter 7.1 of our textbook covers how to solve problems, and you will notice that there is a section called divide and conquer as a technique to solve problems. But divide and conquer is just what we've been doing. I'll read through this. The approach applies the concept of abstraction. Divide and conquer is abstraction that we discussed in chapter 1. So, cleaning the house is a large abstract problem made of the subtasks defined by cleaning the individual rooms. But then cleaning the individual rooms is another abstraction that may have details such as straightening the dresser, making the bed, vacuuming the floor, etc. So tasks are divided into subtasks, which then can be further divided into more subtasks, subtasks it says here, etc. So the divide and conquer approach can be applied over and over again until each subtask is manageable. Once we've got a manageable subtasks, we package that up into a function and we write it. Let's summarize then our lessons from LightBot. First of all, what is programming? It's commanding an agent. What is an agent? Usually a computer, person, or a device that follows the instructions of the program flawlessly, without exception. And what is the program? It implements human intent. Instructions are given in sequence. Actually, a little bit later, we're going to see that you have a few control structures that allow it to change up that sequence, but they're executed in sequence now. There's a limited number of instructions. There's a program counter, and the program counter in the CPU keeps track of the current instruction that is being executed. And finally, what is functional abstraction? Formulating computation as a concept.